Welcome you to this lecture of microscale transport process. What we have been discussing is mixing. We have discussed about several cases. First case was a spot of tracer which is spreading in a resting fluid. So, we have found out the concentration profile, we have found out the expression for concentration as a function of space and in space and time. That expression we have obtained. I have given you the analytical expression, not exactly we have obtained. I have shown you the way and given you the I have given you the final result. The next what we picked up is the spreading of a front, where instead of a spot of tracer, there was a front. That means there are two distinct layers, and one layer is held at certain concentration, another layer at time t equal to 0, the concentration is 0, or concentration is a given value, and then we have found out what would be the concentration, what would be the evolution of concentration in that other layer as a function of time and at various locations. So, these expressions I have given you these expressions, and I have also shown to you the pressure drop in a non-circular channel, because we are more familiar with circular channels, we are more familiar with handling how to handle the, we are familiar with the procedure how to handle the pressure drop in a circular channel, but not exactly I mean we do not encounter on an everyday basis. I mean, so far in your undergraduate or in your undergraduate classes, you have not encountered the flow through a non-circular channel. In this regard, I would like to clarify a couple of points that we discussed in the last class. Number one is that this was pointed out by some student, is that this what we are doing here is we are talking about two different layers. One is of some viscosity and the other layer is of different viscosity, okay, and they are moving side by side, and we are trying to find out how would be the how you obtain the pressure drop in such case. Now, there was a point raised that why we are not considering the surface tension. The fact here is that it is first of all, these two are miscible fluids. If the surface tension would come into play if the two fluids were immiscible. In that case, you have to have, I mean, if you look at here, we are talking about continuity at the interface. We are talking about continuity of velocity, continuity of shear stress. On top of that, you would have you have to equate the sigma. Basically, the sigma is what you have, the stress tensor. I mean, you understand what a stress tensor is. It is basically the tau xx, tau yy, tau zz, tau xy, tau xz. So, similarly, you will have all this is called a stress tensor. I mean, you will have all the elements filled that way. The diagonal elements, that average of these diagonal elements, that gives you the pressure. These tau x's, these are arising if you pick up a differential element, and then if this is the x, y and z axis, then these normal components are considered, they are written as tau xx, tau yy and tau zz, and the cross terms, they are basically the other elements in the matrix other than the diagonal elements, and pressure is given as the average of these three quantities, negative of it. Okay. So, that is how you define. So, this is the stress tensor, and these stress tensor, if it would have been an immiscible phase, then you have to equate the normal component, okay, and you have to bring in that Young Laplace, you have to bring in that Laplace pressure, that delta p surface, that is equal to the delta p surface, that is equal to surface tension, and you have this 1 by r1 plus 1 by r2. So, these things you have to bring in, and you have to consider that aspect at the interface if it would have been two immiscible fluids. But since mixing is possible only if you have two miscible fluids, if you cannot have a mixing between two immiscible fluids. So, I have not talked about it, I have not discussed this. However, this is not a complete equation as far as the microscale transport is concerned, because there if you look at the Navier-Stokes equation, there is an additional term which is typically which is body force, basically the gravity or the Coulomb force. So, there if in fact we will discuss this down the line, something called a Jito potential. There you will have an additional term. You will have an additional term because on the surface, if the channel is very small, what you will have is, if you have a surface and if you have an electrolyte sitting on that surface, there will be some charge developing on the surface, okay, because of say deprotonation of the surface, that is one reason, and because of that the counter ions would be attracted to the surface, and there would be development of one particular ion near the wall. So, that would introduce some Coulomb force in this Navier-Stokes equation, that we will discuss in connection with electro-osmotic flow, but that is missing. So, what you can say is this equation definitely is not complete. This equation is a simple Navier-Stokes equation that we are trying to solve, okay. A simple Navier-Stokes equation that we are trying to solve, and definitely this does not contain all the terms, but when it comes to the surface, the point that you raised is that we should have considered surface tension, but that would be appropriate if you have two immiscible phases, but that is not exactly the case here. But there are other terms that needs to be included in the Navier-Stokes equation. That is all I want you to take from here. But later on, when it comes to the when I introduce this electro-osmotic flow, that time I will discuss the other terms, how that term is introduced in Navier-Stokes equation. In fact, we will find out the pressure profile at that time. So, we have to solve this equation again. The other point that is I think is an error on my part, when I have written here this gamma is flow rate 2 by flow rate 1. I think this is not right. Here it would be, one of the flow rate, say I write it as flow rate 1 divided by flow rate 1 plus flow rate 2. Since it scales between 0 to 1, so I think this should be the case, flow rate 1 divided by flow rate 1 plus flow rate 2. All right. So, that is something which we have. Here, flow rate 1 divided by flow rate 1 plus flow rate 2. So, this is not exactly right. So, make note of this. Okay, so this is as far as the material that we have been talking about. The other thing that we started last time was the concentration distribution in two parallel streams. That means, we have been talking about the flow of two fluids. One is having a flow of two parallel streams. One is having a concentration C0 and the other is having a concentration 0, and they are flowing side by side. And I was pointing out at that time what would be the boundary conditions. Some people have some students have argued with me later that these del C del y equal to 0. Why we are putting it here? Basically, what we are trying to do is that this layer is impermeable. That is all it says. That means, there is no solute moving through this layer. So, it is impermeable. So, flux would be given by d del C del y in y direction. So, that is equal to 0. So, automatically del C del y equal to 0. So, that means, you are treating this as an impermeable wall, this channel wall that is impermeable. That is all that is all I say here. And here I say del C del x at x equal to infinity is equal to 0. That means, at infinity you consider the two streams to be well mixed. So, these concentrations they stop changing. Okay. Now, this equation that I put in the governing as a governing equation, since I put the bracket here, this d does not make sense. So, later on I realized, in fact, this somebody pointed out also. So, please remove this d. I have put an extra d here. This d should not be there. Okay. Now, if we if we try to if we look at this governing equation and we try to find out what the boundary conditions are, okay, what the boundary conditions are. First we need to okay, at the very outset I must say that we pointed out in the last class that this u is having a parabolic velocity distribution. I mean, if you have a laminar flow going on, so at the wall the velocity is 0 and away from the wall the velocity has a velocity would be increasing. So, this u would be changing with y, all right. You would be changing with y, you would be changing with z as well. I mean, I do not know, this side is not open. So, there would be this side also in the z direction also there would be. So, this u is a function that way, but this would not be analytically tractable. I mean, it would be analytically tractable if you consider u to be constant, that is the average velocity. So, that is an assumption, that is a simplification. I mean, always we do some simplification. In fact, when we write this equation also there are several assumptions we make. So, if you consider that to be the average velocity, probably this can be done analytically. Now, if we introduce some dimensionless variables here, say for example, x star which is equal to x by w, y star which is equal to y by w, c star which is equal to c by c 0, and Peclet number which is u bar w by d. Okay. If we introduce these dimensionless variables, then you can write this as Peclet number del c star del x star, that is equal to del square c star del x star square plus del square c star del y star square. So, this is what you have, and then if you try to write the boundary conditions now, the boundary conditions would be c star at x star is equal to 0 and y star in between 0 and gamma. What is gamma now? Gamma is equal to m1, or you can write this as q1 divided by q1 plus q2, that same way that we have defined earlier. Okay. So, this is between, this value of this gamma is between 0 to 1. So, this c star, this is equal to 1 and c star x star is equal to 0, gamma y star 1, this is equal to 0. So, at the inlet, the stream that is having either it will have a higher solute concentration which is in a dimensionless form, that is equal to 1, and the one which has the lower or the 0 solute concentration, that would remain 0. So, all these two conditions are valid for x star equal to 0. Okay. So, this is at the inlet. So, this is at the, this I have written is at the inlet. Then we have another wall condition. Wall condition is that del c star del y star at y star is equal to 0 comma 1. See, w is in y direction, y is equal to 0 here and y is equal to w here. So, w is in y direction. So, it is between 0 to 1. So, y star is equal to 0 or 1, both are walls, and this is the wall condition. If somebody is working with multiple streams, that means one C0, another stream with 0 concentration, then there is another C0, another 0, another C0, another 0. Okay. If you have multiple such streams, then probably by symmetry, I mean, it will not be a wall condition, but you will have a similar condition by symmetry, because by symmetry this derivative of concentration with respect to y star would be 0. then other condition is at infinity. Other condition is at infinity, and there you have del C star del x star at x star is equal to infinity, 0 less or equal to y star less or equal to 1, this is equal to 0. So, by this time, by the time the stream reaches infinity, the two streams reach infinity, there, I mean everywhere, whether it is y is within 0 to gamma or gamma to 1, everywhere the concentration is well mixed. So, concentration will stop changing. So, these are the boundary conditions, and this is the governing equation. Now, this I wrote this as Peclet number. This is on the basis that you are writing it as u bar. If you write it as u, then probably it will not be, you cannot write it this way, because Peclet number is defined as u bar w by d. All right. So, this is what you have. Now let me tell you that these C, if somebody wants to find out what is C star as a function of x star comma y star, this is available. I mean, you can solve this using separation of variables, and you can come up with some kind of it would be an analytical expression that is possible. Okay. The other way is that you consider a velocity profile here u and solve it numerically. So, that is also another possibility. So, this is something which is I mean, I am not indicating here the exact analytical form, because it's really it's a long expression, and but just be aware that these analytical expressions are available. Now, what is important here is that how much suppose you have a solute stream here, this is the solute and this is the solvent stream. Solute means solute, it is not a solid solute, it is a high concentration stream, and a stream which is, so it is basically is a saline water, another is pure water, and salt is diffusing from solute stream to the solvent stream. So, here you have, if you look at, suppose then in that case this is, suppose this height, of course, this height does not matter as such. What I try to point out here is that you have a diffusion of solute from this layer to this layer. So, as the two streams coming here, so these two streams they were well separated, but when it arrives here at this place, you will find that there would be a diffusion that has taken place. If this is the center line, a diffusion that has taken place, which suppose this is the solute layer, you will find that this portion the solute has penetrated. And can you so these portion you want to call, say, delta wall, the distance by which the solute has penetrated. Okay, of course, you would ask me how do you define the penetration of solute. I mean, it would be anyway, that would be a very continuous change. So, how you define? So, that is something like the way we define a boundary layer thickness. So, it would be, I mean, it would be a similar concept, I guess. Now, this at the wall the penetration is say delta wall, and at the center the penetration it say it is delta center. Now, the question could be that why such a profile, why it would be it is taking such a shape, why it is not straight. Why this is taking such a kind of shape? I mean, initially when you started, the solute was half of it is occupied by the solute stream, half of it is occupied by the solvent stream. When it arrived, you see that this portion the solute has penetrated more and this portion solute, but probably you might have already thought about, I mean you must have already gotten the answer. I mean, let me point out here that this is the slowest moving layer because it is next to the wall. So, this is the slowest moving layer. So, this layer is moving slowly and this layer is the fastest moving layer. So, how much time it is getting for the diffusion to take place? So, it depends on that, right. So, this is this portion, the layer, that stream that is coming at this place, it is probably it had least residence time inside the channel. So, that is why you do not you cannot expect the diffusion of solute to penetrate far into far into the layer at that place. So, this is how it is done. Now, what people have done is what researchers they have done is they have numerically found out that this delta center they have numerically found out, and this delta wall they numerically found out. Okay. I mean you can but to have this you cannot consider u to be the average u. You cannot consider u to be the average u. You have to consider the actual u. You have to consider the velocity distribution, okay, and then you solve numerically and you find out how much the penetration would be. So, from there you can calculate delta center as a function of x and delta wall as a function of x, and as a matter of fact somebody has done, some researchers have done experiments also on this. So, basically this delta center, and then they have tried to find out how this proportionality would be with reference to d, with reference to x, with reference to u bar, with reference to h. What is h now? H is this height, okay, and x is this direction, y is this direction, z is this direction. So, that means if this is y, so from the old one that we have here, there we have, if this is the y, so then, and this is w. So, if that is the way we have done earlier, so then this would be equal to w. This would be equal to this distance would be w, this distance would be h, and this would be the x, y, z. So, this proportionality they try to find out how these delta center as a function of x and delta wall as a function of x, how they depend on these quantities. Okay. And what they found is basically this is proportional to d to the power half, this is proportional to x to the power half, and this is u bar to the power minus half, because if you have an average velocity which is higher, then automatically you are giving less residence time. So, automatically the delta center would be less, it is that way. Similarly, delta wall also they found that this is d to the power half, x to the power half, h to the power half, and u bar to the power minus half. So, that is typically the trend that has been established experimentally or numerically. All right. So, these are some of the things that h is this height. Delta center does not depend on h. Delta center does, I mean that's what the results showed, that delta center does not depend on h. Anyway, so this is what we have. Now, I want you to I mean all these things, these are actually very, these are not exactly related in any way, in a sense that what you are in, what we are interested in here is that we want to accomplish mixing. And of course, if we have two streams flowing side by side, at the very outset I told you that it is not possible. You require 1 meter, you require 1 meter, 100 meter, that kind of length to accomplish a mixing this way. So, it is not at all going to, I mean in fact, the next topic that I will pick up, that is, in fact, if you look at in the slide, what you have here is sequential lamination. Okay. Sequential lamination is this segregates the joint stream into two channels and rejoins them in the next transformation stage. This is also known as split and recombine mixer. So, this is something which we would be doing, this is something which we would be discussing. So, in the microchannel our objective would be to split the stream and again recombine, but when if the two streams happen to be flowing side by side, these are some of the aspects that you have to bear in mind, that you have to keep at the back of your mind, that these are the few things that are going to happen. Okay. So, the next topic that I pick up now is sequential lamination. Sequential lamination. Sequential lamination is that you, let us see, suppose I have two streams coming here. One is your so called solute stream and the other is solvent stream. Okay. Then what you do here is you pick up half of it. I mean, when you carry this, the way this lamination is done is you pick up half of this stream to this direction and the bottom half you are taking in this direction. Okay, so, you have the internals inside the channel such that the bottom half is completely taken through a detour and this top half is taken as a detour, and then they are delivered in one place, but this time when they are delivered they are not put as top or bottom, they are put as side on the, it's like one on the side of the other. So, what you get is this. I mean, I do not know how much I could explain here. The point here is that you started with one solute and the other solvent stream, pick up the top half through a detour. I mean, this is done entirely. So, this is the channel, basically this is the channel. You do not see what is going on inside, but inside through the internals what you are accomplishing is you are picking the upper half and delivering it, and the bottom half you pick up through a separate detour and delivering it, but while delivering you are delivering them as side by side. So, that means it would be the after delivery this is the shape it is taking. Then you go, you repeat the step, then this would be multiplied. So, here one solute, one solvent, here I have two solute and two solvent, the same thing would be repeated down the line. Okay. So, this is something which we were talking about is this is called sequential lamination and also referred as split and recombine mixer. Now, if we try to find out, and now we try to find out the theory of it, what we see here is that you have a time dependent striation thickness. We call this say WT, this is W0. So, at t is equal to 0 you have a striation thickness, we call this say W0, and this thickness is going down, it is becoming smaller. So, we call this a time, because if it continues with the time, so it is a time dependent striation thickness, we call this WT. Okay. And W0, W0 you can call this a half width of the microchannel, then I mean to start with. I mean it depends on how you define W, it could be either half width of the microchannel or you can call this the full width of the microchannel, that is how you refer W, but my point is that this W is going to decrease with time. Now, how the W changes with time. So, if somebody wants to write say I mean, what I am going to do next is I am going to define something called a stretching function, which I will call alpha t, and this alpha t is equal to minus of d ln w t dt. This is what I call the stretching function. That is how this is defined. Why are we getting into this ln w t? Okay, there is a history to it. When it comes to stretching, there are two types of stretching possible. One is called elongation stretching, and the other is called linear stretching. Okay. Now, this linear stretching is something which we are familiar with. This linear stretching is the stretching that we see in a viscous layer. The stretching that we see in a viscous layer. What is this stretching? I have one layer next to the wall which is having velocity 0 at under no slip condition. The next layer is moving at a higher velocity. So, you are doing some kind of stretching. You basically see my objective of putting this sequential lamination is that my objective of putting this sequential lamination is that I have to take 2 points which are adjacent to each other from one place to other. I mean, suppose it is like I started there was a point say here, and there was another point say here, and there was another point say here. These 2 points are neighboring points. Okay. Objective of this mixing is that these 2 neighboring points, they go away from each other. Then I will consider that mixing has taken place. If the 2 neighboring points remain as 2 neighboring points, then I do not think then that is helping in mixing. So, this stretching function, when we are introducing, we are trying to find out how these 2 neighboring points are stretched. Okay. Now, when we are talking about this linear stretching, this is the stretching that we encounter in a viscous flow. That means, one layer sliding against the other, that is also stretching, because one point which is next to the wall and the point which is away from the wall, or maybe the point, one point which is somewhere near the wall and another point is next door. Now, these 2 points, because of this velocity gradient, they are moving at different velocities. So, I am having a stretching. These 2 points are flowing at different velocities. So, if I consider say T f some finite time, after some finite time I will see that these 2 points are located at different places, and the distance between them, I mean, we are considering that stretching. That stretching is referred as linear stretching. Why it is called linear stretching? Because I can write W 0 by W T f. T f is some finite time or final time, I call it. So, at the end of the event, the striation thickness is W T f, and at the start it is W 0. This is close to gamma dot T f. What is gamma dot? Gamma dot is that shear rate. Gamma dot is equal to the shear rate, that is equal to du dy, that is equal to y u by h. These are various forms we have. So, this is called the linear stretching. This kind of stretching we understand, we do it frequently. If we have a viscous flow going on between 2 layers, this stretching is possible. On the other hand, this elongation stretching is W 0 by W T f, that is equal to exponential of alpha T f. Here the W 0 by W T f, this is not a linear function, rather it is an exponential function Here with time it is basically linear. Here we have an exponential function, and this alpha is this coefficient. Okay. So, this is how this W0 by WTF, W0 is the striation thickness at time t equal to 0, WTF is the final striation thickness, that is equal to E exponential of alpha TF. Okay. Now, what is the origin of this elongation stretching? I mean, this linear stretching I could understand, it is basically typically the stretching that we encounter in viscous flow, but what is the origin of this elongation stretching? This elongation stretching arises from the process which is referred as chaotic mixing. Okay. Chaotic mixing. Let us say dx dt is equal to u as a function of x and t relates position x t of the fluid particle. Okay. A solution to this equation, which is probably what you are looking at. So, the solution to this equation is considered chaotic if the property of this, I put quote unquote, sensitivity to initial condition is satisfied. What this, I mean, in their terms, what basically this statement means is that two neighboring particles they diverge on average at an exponential rate. That means two neighboring particles, we started with two neighboring particles. If we had a linear stretching, then I know that one layer is static, say maybe fixed close to the wall, and other layer is the next layer which is moving at a somewhat higher velocity. So, after some finite time I will find that one layer has traversed up to this point, whereas this layer is still static, or maybe with reference to this layer there was another layer which was here, and then you will see that this layer has gone further there. So, there is a linear stretching. So, these are some of the things that are happening. Now, this was the linear stretching, but this here the two neighboring points, they are moving away from each other on average at an exponential rate. So, that is basically the elongational stretching that we had, W0 by WTF, that is equal to exponential of alpha TF, that is what this says. So, this is referred more as the chaotic mixing. When somebody prepares a dough for making bread, that they are probably, if you put two colored points on that dough, and when that person who is making that dough, when he is stretching it, the type of stretching that you get is chaotic, is probably this elongational stretching that we are referring here. Now, you cannot, ideally you cannot have all chaotic mixing in a real mixer. In a real mixer, you will have some places which are called islands, and these islands will have these islands as a whole they translate. So, in a real mixer, the microfluidic mixer that a person will fabricate, person in the using this microfabrication technique, the microfluidic mixer that is made, there you will have so called island which is undergoing translation, undergoing rotation as a whole, okay. And within that island you can expect this linear stretching to happen, and outside these islands there would be these chaotic there would be these elongational stretching. So, in this mixing process it is a combination of both these stretchings, and so in a real microfluidic mixer what you would expect is an island or few islands moving by translation, they are rotating and everything, and within the island the linear stretching is going on, and outside the island it is chaotic mixing. So, that is something which is going to happen. Now, what will I do with this alpha? What is the purpose of this alpha? Okay. What I would do is then in what I will try to find out is that in local coordinate system of striation, I mean we try to get into this Lagrangian, I mean we are trying to invoke the Lagrangian sense here in local coordinate system of striation. That means, I pick up this striation and I am treating this as if it is a Lagrangian particle. Then in the local coordinate system of striation, the normalized diffusion equation would be del C star del T star, that is equal to del square C star del X star square, okay, where, I mean C star is understandable, C star you can always make it from C by C 0, that is not a problem. The way this diffusivity is taken in this T star. So, X star here is X divided by W T, okay, and T star here is equal to integration 0 to T d divided by W T prime whole square dt prime, okay. And this W T prime, so you will be writing it as integration 0 to T d divided by W e to the power minus alpha t whole square dt prime. Let me point out once again what we are doing here. You think about just one striation. This is called a striation. Now, if I pick up this and I try to find out how much of diffusion is taking place in this layer, if we pick up, if we take this one and if we try to find out how much of diffusion is taking place here, so I treat this as a, I mean as I said, in a Lagrangian sense, okay. So, what I do here is I write in local coordinate system. So, within this local coordinate system, see how this x is defined. I started with this as W0 and I said that this is changing, this thickness, this striation thickness is changing, it is becoming, it is W0 now and it is going down with time. So, at some arbitrary time it would be Wt, and there in that Wt, using that Wt I am defining here the X star, using that Wt I am defining the X star. So, this X star is the local coordinate system within that striation. So, I am treating that as a Lagrangian particle as it travels. Okay, so x star is x by wt, and t star the time. Here I am defining the time this way, that t star is equal to integration between 0 to t d divided by wt prime whole square dt prime. So, over this between time 0 to t, what would be this value, sum of d divided by wt prime whole square. That is how we are defining t star. Okay. So, now if you bring this whole thing into x t space, this is a Lagrangian space we are talking about. So, we have defined this x star. Okay. Now, if you come to the actual the mixer coordinates, if you bring it, this would be, you know that diffusivity scales to delta x square divided by t, where delta is the penetration. Let us drop this x. Let us call this just delta square by t. This is how diffusivity scales. That means, definition of diffusivity is that how much it penetrates, how much the solute would penetrate, the square of that divided by time. Of course, this is I mean the penetration itself, you have to follow the governing equation. I mean, ideally, if you know already that if you are really solving the diffusion problem, then ideally you need to solve del c del t is equal to d del square c del z square and all these things, and solve this. It is not that straightforward that you can write d is equal to the penetration square by time, but when it comes to the scaling, this is the form that is followed. This is the scaling that is followed. Okay. So, for some quick estimate, probably this is something which could be handy, but definitely not a rigorous mathematically rigorous method. Now, d scales to delta square by t. So, what you can write here is that delta by wt is close to is of similar order to t star to the power half. Okay. And this wt, what you would be writing here is delta divided by w e to the power minus alpha t, and that is, if we instead of, or you can continue this way, this is equal to d divided by w square 2 alpha into e to the power 2 alpha t minus 1 to the power half. How do you get that? You bring in here this one. Now, t star is equal to integration 0 to t d divided by w e to the power minus alpha t whole square dt prime. Now, you do the integration here. I am little bit the only thing is w e to the power alpha, here it should be alpha t prime. Okay. So, you do the integration here, you do this integration, I write it clearly 0 to t d divided by w e to the power minus alpha t prime whole square dt prime. You do this integration and then put this here as t star. So, this is equal to t star. So, this t star has to be put there, and then you can you will get this expression automatically. You have to go and check this whether you are getting this expression or not. All right, this t star is referred as this is different from time. So, this t star is referred as warped time, and this x star x star is defined as striation thickness best space. Striation thickness best space. So, this x star is defined as striation thickness best space, and this T star is referred as warped time, and if you bring in this delta by W t, then this would be the case. I do not expect you to immediately understand all the aspects of it. You have to, what you have to do is, you have to, after the class, you have to go back and play with these expressions. I have given you all the threads. Now, you have to play with these expressions, and then you have to come back to me maybe in the next class, that what you have, what objection you have to these expressions, because I have given you all the threads. Now, you have to assimilate it. Okay, it looks like I mean, I am putting things not I mean, I'm because this concept is something which is a little different. So, that is why I suggest that you go through these once again, think about what is going on. This is basically a local coordinate system. Think in that line, that you are picking up this element which started it started with W0, or I think when I write this W into e to the power minus alpha t, automatically this W is W0. All right. So, this W is W0, but I cannot put so many things in bracket. So, it is better if you put this as consider this as W0, that is the width at time t equal to 0. Okay. So, this is something which you need to play with and see whether you end up with this expression or not. All right. So, one thing I must point out, that this is not this is elongational mixing, the theory that I am discussing here, because at the very outset we said it is e to the power minus alpha t. The moment e to the power minus alpha t, the moment we put this, it is elongational stretching, and this elongational stretching is not everything. There are other forms of stretching that is also available, and probably in a real mixer it is a mixture of both. Because one thing you must understand, that I mean, I can say that two neighboring particles, they diverge on average at an exponential rate, but how long they will continue? I mean, if you look at a dough a baker is making, preparing, there you are stretching 2 points, but then the baker has to fold it again, right. So, if you assume that they will continue to expand, if the distance between them will continue to expand in an exponential manner, it is up to some time, and then again there would be a folding. So, it is basically we are trying to put together the elements of mixing here. This is one element of mixing, which is called chaotic mixing. The other element is linear stretching, and the mixing that you would see in a real mixer is the sum of or combined effect of all of them. What I will do probably in the next class is I will probably I will try to extract some more information from this equation that I have here, and then I will discuss a topic known as sequential segmentation. This is something which I would pick up. Sequential segmentation. This is also another form of mixing. Where a solute stream, there would be two streams coming in, okay, and there would be an on off mode. On off mode means, suppose this is the solvent and this is the solute. So, this solute goes in and then it switches off, solvent comes in, then again solute goes in. So, at the end you will see there are blobs of solute, okay, and then you allow the mixing to take place between solute and solvent. So, that is a sequential segmentation. This has its own theories. Basically, it would be a boundary condition where the I mean the governing equation would be again same, that same equation that we have been talking about, del c del t is equal to d del square c del z square, or in a two dimensional flow we have already discussed. Our basic framework is that same diffusion equation. however, we play with the boundary conditions, and we will show you how we can get the concentration profile in this case. So, I suggest once again that you go through these chaotic mixing the expressions, and probably think over it, and then let me know what problem you see, or what is the problem with these expressions, and then we can probably go from there. That is all I have for today's class.